Let's calculate our first limit in multiple variables. This expression as the two variables x and y go to 0, 0. Now the naive thing to do is to simply put in the value 0 for x, 0 for y, that is to substitute, or plug in as I've heard it called in the past. This is a mistake. That is the one thing that you do not want to do when calculating a limit. The whole idea here is to only talk about the properties of this ratio for points x, y that are close to 0, 0, but not at 0, 0. If you simply substitute the numbers 0 and 0 for x and y respectively, then you are assuming the thing which is to be shown. Okay. So how can we talk about this? The limit as xy goes to 0, 0 of this expression can be calculated. I'm going to choose a direction. And now, I'm not going to choose one direction, I'm going to choose two. Okay, the directions are going to be the directions on the line. I'm just going to put this in parentheses one time. That is the solution set to. Okay, and I need an algebraic equation whose solution set is a line that passes through 0, 0, and I want it to have arbitrary slope. I could write this as y is equal to mx minus x0, end parentheses. Here, I'll do it. See, this is the line with slope m, an arbitrary slope, that passes through the point 0, 0. Okay, now of course there are two directions along that line. Pardon my cold. Now, the idea here is that this equation, y is equal to mx, allows us to rewrite this expression. If we're only looking at points on the line y is equal to mx, we could rewrite this expression as 3x squared minus m squared x squared. See, I've replaced y squared with m squared x squared, or just replaced y with mx. Similarly, in the denominator, x squared plus m squared x squared plus 2. And that goes to 0 plus 5 over 0 plus 2, which is equal to 2/5, or 5/2 rather, as x goes to 0. Now, of course, in order to really show that this is the case, we would have to do a delta epsilon proof for a limit in a single variable. But we're going to be fast and loose on this part, for the sake of time. Okay. Now we can see that this is independent of m. All right. Let me try to finish off this sentence. This limit can be calculated along either direction on the line that is the solution set to y equals mx by observing that this is the case. Okay. Now, from there, I want to say, since this is independent of the slope that I chose here, m, the limit is independent of direction. There's the n in sense, I think. independent of direction. Thus, this whole limit going to 0, 0 of 3x squared minus y squared plus 5 over x squared plus y squared plus 2 is 5/2. Now, just to visualize what I mean here, let's take the xy plane. The lines that I'm talking about here, the lines that are the solution set to y equals mx for various values of m, they're these various lines that pass through the origin. And in fact, I get every line except for the vertical line. Well, what would the vertical line look like? The vertical line is y is equal to 0, right? Rather, x is equal to 0. So if I were going to consider the paths, the directions that are along the line, that is the solution set to x is equal to 0, then what I would do is set one of these two variables, x, to 0, and then calculate the limit that y went to 0 also. Now, I'm just not going to be quite that careful. You get almost every single direction by of possible approach by looking at lines of the form y is mx, or y is m times x minus x naught plus y naught. And that is as careful as we need you to be at this point. I'll make another video where I go over the delta epsilon proof of this, because none of this was really particularly rigorous.